Dear students, in this lecture we will study root test for convergence and divergence of series of real numbers. Let us study root test. Series AN is a series of real numbers. Then for this series of real numbers we define A as A is equal to limit superior of the sequence nth root of mod an, nth root of mod an. Then the test states that if limit superior is less than 1, then series converges absolutely. If limit is greater than 1, then series diverges. So it diverges when a is greater than 1. It converges when a is greater than 1, and if a is equal to 1, then in that case test cannot be applied. Test fails. It cannot be applied. So let us see proof of these results one by one. First, a is less than b is less than 1. In first case, our hypothesis is that a is less than 1. This is our hypothesis. So choose a real number b such that a is greater than b but less than 1. So a is less than b and b is less than 1. So b is greater than b is greater than b is greater than superior. B is greater than superior. Limit superior. Limit superior. So by known result, there is a positive integer n such that whenever n is greater equal to n, limit superior of which sequence? Let me write it here. It is mod an. So by known result, there is positive integer n such that whenever n is greater equal to n, nth root of an is less than b. This implies that n is greater equal to n implies mod an is less than bn. So the series mod an is dominated by series bn. But the series bn diverges as b is greater than 1. The series converges as b is less than 1. So as b is less than 1, the series b raised to n, it is geometric series and it converges. In fact, we have b is positive and it is less than 1, so it is convergent. So by comparison test, if a bigger series converges, that is bn, then a smaller series also converges. Hence, this series converges absolutely. That is, in notation form we can say series mod an is less than infinity or it is summable. So this is the proof of first part. Now let us go through the proof of second part. In second part, our hypothesis is that A is greater than 1. A is greater than 1. What is A? A is limit superior of the sequence mod an. It is nth root of this sequence. Okay, so nth root of this sequence means A is, it means that there are infinitely many values of n for which nth root of an is greater than 1. We have studied several results on limit superior and inferior, and by using one of the results we can say that as it is greater than superior, that is greater than 1 is less than superior, so there are infinitely many values of n for which nth root of n is greater than 1. Note that 1 is less than limit superior of the sequence nth root of mod an. That's why we could write this. Now, if there are infinitely many terms of the sequence which are greater than 1, it means that series is definitely, it means that the sequence will not converge to 0 because there are infinitely many terms of the sequence which are greater than 1. So by necessary condition for convergence of series of real numbers, we can say that series diverges. This gives us the proof of second part. Note that we are using necessary condition for convergence of series of real numbers. Series of real number converges, then limit of its nth term is 0. As here limit is non-zero, series an is divergent. Finally, to prove that test fails when a is equal to 1, it is sufficient to give two series for which one series is convergent and other series is divergent. So for both of these series, a is equal to 1 for this series as well as second series 1 upon n square and harmonic series. However, this series, it is p series with value of p equal to 2, it is greater than 1, so it is convergent, and we know that harmonic series is divergent. So when a is equal to 1, we have two series for which one of which is convergent and other is divergent. So test cannot be applied for convergence or divergence because it may converge or diverge when a is equal to 1. This was the root test. Root test practically we apply in this way. We find nth root of sequence an. If limit exists means limit superior also exists and it equals to limit. So if value of limit is less than 1, then series is convergent, and if value of limit is greater than 1, then series is divergent. Which series? Series mod an. It is convergent and it is divergent when limit is greater than 1. So when limit is greater than 1, it is convergent, and when limit is less than 1, it is convergent. Thank you.